Hello, everyone. My name is Zheng, and I come from Rice University. Now I'm a master computer science student. And in this summer, I participate in a project called pyhf hardware acceleration benchmarking with CPUs and GPUs at IRIS-HEP. And my mentor is Matthew Fakert. Now let's get started. First, I want to introduce my project. Before I introduce my project, I want to first introduce a library called pyhf, which is a pure Python implementation of the histofactory statistical model for multiple being histogram-based likelihoods. And in this summer, I developed a library called pyhf benchmark, which is a benchmarking test suite in Python to test and benchmark the performance increase of the hardware accelerated backends, such as TensorFlow, JAX, Pratyush, and stuff over GPUs and CPUs on the openly published physical data from LHC experiments. Next is the summary of my work. I wrote monitoring codes for the performance of CPUs and GPUs based on NVIDIA management library, and wrote comparison plot generation codes using matplotlib. Then I made the library be a pip installable package and supported Python API as well as the command line API. Then I added unit test for pyhf benchmark package. And last, I create a documentation using Phoenix that is deployed as a public website. In the next step is the research and solution of my project. In the beginning phase of my project, I did a lot of research, and finally, I decided to use the following system metrics during benchmarking, such as the CPU utilization, system memory utilization, GPU utilization, and GPU memory allocated, and stuff. Well, all of these system metrics are provided from the NVIDIA management library, which is the standard measurement of CPUs and GPUs provided by NVIDIA company. And it is a C-based library. And fortunately, I find a third-party Python library, which can help us to capture the system metrics successfully during benchmarking. And I also noticed that hot machine learning benchmarking suite called 1DB package also use all of these system metrics and get success. So I think this approach is feasible for our projects as well. And the third step is the achievement exhibition. Well, all of the users can get the source code and the README introduction from the GitHub link. And the users can install the pyhf benchmark using the following command lines, and the PyPI installation is coming soon. And the users can also use the Python API in the future. Now the users can use the command line usage. The following are the command line usage, and the following lines are the examples. Well, more details about the command line usage and the examples can be found over the GitHub link. Next, I will introduce the files the users will get after they use the pyhf benchmark. Well, on the left side, it is a snapshot of the file structure. The first part, you can see that all of the files will be stored under a directory called the output. And under the output directory, the first level directory will be named as the run following two series of digits. And the first series of digits means the days the user run the pyhf benchmark. And the second series of digits means the time in milliseconds that the user run in that day. And the second level file directory is named as the name of the data, following by the computation type, and following by the backend type. Well, the users can get all of the system metrics graph plots they wanted under the second level file directory. And for example, on the right corner side, you can see example graph. The x-axis are the time, and the y-axis is the CPU utilization. Well, so the users will get a lot of graphs with the x-axis with of time and the y-axis as the system metrics I mentioned before. Well, in addition, users can also have the flexibility to run several backends over the same dataset and the same type of computations at the same time. And in this case, all of the graph plots will be stored under under the different backends directories, and all of the files will be stored separately. And the combination graph plots files will be stored under the first level file directory, and you can see examples here. And another example of the plots will be shown on the on this picture, and you can see that it is a combination graph plots of JAX and NumPy. Well, besides, the users can get another very important metadata files called event.json file, which stores all of the system metrics and timestamps. Well, the users also have the right to set the time interval as they will. And for example, the default time interval now is 2 seconds, which means that our program will monitor the performance of CPUs and GPUs every 2 seconds. And one item will be read back to the event.json file every 6 seconds, which means that the system metrics will be averaged every 3 times, and it will monitor the performance every 2 seconds. The users can have, in this case, the users can have the right to plot whatever
Well,
the.
you don't have to have air blowers to have it be touchless, right?
Sorry. Okay. Well, in this case, your users can plot whatever combination plots they want using the metadata file. And last is the feature work. I summarize the feature work as 3 independent points. The first point is that users can perform benchmark test cases for the model analyzing different hardwares. And the second is that current research on TPUs is limited to the evaluation to the performance of TPUs on Google Colab platform. And more details can be found on GitHub issues. So I think more research over TPUs is needed. And the last point is that I have wrote the code for plots visualization on websites using D3 JavaScript and Flask. I think further optimization of a nicer data visualization can be taken if needed. And last is my first feature plan. I will go back to the Rice University for a master's degree of computer science and look for a software engineer full-time job after graduation. That's all, thanks.
Thank you, Bo. Anyone with any questions or comments? No? Okay, thank you.
Yeah.
Thank you, Bo.
Okay.
Yeah, I'll just say thanks very much, Bo, for his nice fellowship work, and we very much appreciate it.
Okay, thank you, Matthew. It's
Thank
my
you, Matthew.
pleasure.
All right. Moving on. Next up, we have Peter Chatain, who's going to talk about his project track seeding in ACTS. Peter?
All right. All right, can you guys see that?
Yes.
Okay. Hi, so my name is Peter Chatain. I'm a junior at Stanford University, and my mentors were Dr. Rocky Balagarg and Professor Lauren Tompkins. So my project was to code a track seeding example for the open source project ACTS. And to best explain, I'll briefly review tracking and the goals of ACTS. So inside a particle collider, when the particles collide, thousands of other particles are created. And the charged particles, as they move through the detector, they create hits, or what's called space points. And these simply contain the XYZ coordinates of where that particle was at that time. And so tracking is the process of taking these hits to reconstructed particle trajectories. And because there's a magnetic field inside of the detector, the charged particles will move in a helical path. And on the left here is a diagram of some example hits and then some example tracks of what the track finding algorithm will try and do. And so one strategy for tracking is to break into two parts. The first part is track seeding, and the second part is track following. So seeds are tracks with only 3 hits, and they're basically tracks normally have about 6 to 14 hits. So they're very similar. And seeds provide an initial estimate of tracks. So in the bottom left, you can see an example where the red lines represent seeds and then the blue lines are the tracks. And a lot of the seeds in this example, you can see don't actually correspond to tracks. And so when the seeds are like propagated forward, if there are no hits found in the later stages of the detector, then that seed basically will get discarded. And so I just want to talk a little bit about how the seed finding algorithm actually works. So the space points are grouped into 3 different bins, and for each middle space point, they have a search window over the top and bottom space points, and then every possible combination of top and bottom space point, a seed is created out of that. And then the seed is checked for compatibility with a helical path. And if it doesn't match a helical path, the seed gets discarded. And it's really important to discard certain seeds because, as you can imagine, the combinatorial, the combinations will explode as the number of space points increases. And then also the seeds are ranked according to a score, and then seeds that have a low enough score get discarded from the seed finding algorithm. And so why do we need faster algorithms? Now, the high luminosity LHC is planning an increase in data production per event by a factor of around 5 to 7. And this creates a problem because the current algorithms, their compute time will explode when this happens. And so part of the goal of ACTS is to help develop these faster algorithms. And so the code is written in thread safe, and this allows for parallelization, and it's also written to be maintainable. And so it uses modern C++ advantages, such as const correctness. And then what's really challenging is that they want to allow these advantages in the tracking algorithms to be used on different detector geometries. So ACTS has implemented a generic detector, and then they want to be able to have the algorithms run on many different detectors. And this is really challenging because a lot of the algorithms depend on the specifics of the detector geometry. And an example in ACTS is its functionality that allows for testing of individual components of tracking. So for example, my project allows for testing just the track seeding part of tracking. And previously, the tracking example did not use the seed finding algorithm. It used truth information. And so once my project is complete, it allows for a complete tracking example. And to run my algorithm, you specify an input directory with your simulated data, and then an output directory where it writes performance plots. And then it also prints out some basic statistics on how the algorithm performed. And so efficiency is defined as the number of particles found by at least one seed. And this is really important for seeding, because if a particle is missed in the seeding stages, it won't be found in the tracking stages. And then fake rate is the fraction of seeds that don't correspond to a real particle. And this is important to keep low, because if fake seeds are passed on to the track following stage, it'll increase computation time. And then similarly, duplicate rate, which is defined as the number of true seeds that find a particle that was already found by another seed. This is also important to keep low, because it'll increase compute time. And so before any optimizations, I just wanted to highlight that the algorithm did not perform as well as it should. And so the efficiency is ranging here between like 20% to like 80%. And we really need it around 99%, which is how it performed on Atlas, which is where the code was imported from. And so I tried to optimize it, just preliminary optimizations for the generic detector and ACTS. And some of the things I did were I moved the beam position to 0, 0, because that's where it is in the generic detector and ACTS. And I also adjusted the radius so that it matches the radius of the inner detectors, the inner pixel detectors in ACTS. And then I also increased the sigma scattering, and that allowed for a higher efficiency, but it also allowed for more seeds to be generated. However, the efficiency still wasn't looking quite right, so I took a look on a different sample. So when we looked at a sample generated from a single muon gun, we found a really strange pattern. So we'd expect the seed finding algorithm to perform better for higher momentum tracks, and we pretty much found the exact opposite trend. And when I looked into the seed finding algorithm, I found that one of the cuts on the seeds was not optimized for the ACTS geometry. And so by simply just removing this cut on the seeds, we got the expected efficiency. However, the number of seeds generated was way too large. It was on the same order as the number of hits, actually. And so this cut still requires tuning. And then after this cut is tuned for the ACTS detector, the configurable parameters that I edited earlier will need to be retuned again. And so just to briefly overview some specific work that I did, I wrote a function that converts the data into space points. And then, because this is what the seed finding algorithm runs on. And then I also converted the seeds from the algorithm into proto tracks. And there already were performance tools written for track finding. And so they ran on a data format called proto tracks. And so this allows for utilizing those analysis on the seeds. And then there's still some differences in how we want to analyze seeds. And so I wrote a particular function for seeding that categorizes seeds as true or fake. And then I also, we don't expect all of the particles to be found by seeding. So I wrote a function that filters on whether we expect the particle to be found, and that allows for a more accurate measurement of the efficiency of the seeding algorithm. And then I also, it also outputs the performance plots that we saw earlier. And then my code is currently undergoing review with Xiaosong to add my example to ACTS on GitHub. And I'm working for about another week and a half. So some further work to do is, as pointed to earlier, since we're trying to change these configurable parameters, a better way of doing it instead of just going into the code and actually like changing the magic numbers is to develop a more, to develop an optimization pipeline. And so getting the configurable parameters outside of the code so that they're read in would help with that. And then also clustering, which is the particles can sometimes create several hits all clustered in one little area. And then the seed finding algorithm can consider these, all of these points as separate points from potentially different particles, but we don't want it to do that. We want it to consider all of these hits generated from one particle. And so that's what clustering is. And currently this isn't done, but once it is, it'll reduce the number of duplicate seeds generated. And thanks for your time. Are there any questions?
Thank you, Peter. Appreciate the presentation. Anybody have any questions or comments?
I'll make the comment that it was really a pleasure to work with Peter this summer, and we're looking forward to getting this into the ACTS master branch.
Thank you, Lauren. Again, thank you, Peter. We'll move on to the next one. Next up, I'm not muted. Okay. Next up, we have Pratyush Das, who's going to talk about translating scalar CPU kernels to vectorized GPU kernels for the awkward array library.
Hey,
Pratyush,
should I share my screen? Yeah.
Yes, please.
Can you see it?
Yep.
Okay, great. Hello, everyone. My name is Pratyush Das. I'm a senior at the Institute of Engineering and Management in Kolkata, India. This summer, like all of the speakers before me, I was an IRIS-HEP fellow, and I was working with Anish Biswas, who's a Google Summer of Code student, under the mentorship of Jim Pivarsky on awkward array. So, some of you in the audience might already know me. I have been working with Jim for around 4 years now. We started off in 2017 working on Root4Gen Spark Root. I worked on Uproot for 2 summers, and this summer I was working on awkward array. So for those of you who are not familiar with the awkward array library, it's a library for handling jagged arrays in Python. So initially the awkward array library was deeply integrated with Uproot, which you might have heard of, before it was pulled out as a separate library. And last year it was rewritten in C++ with a Python wrapper around it. So the goal of my project this summer was adding a CUDA backend to the awkward array library. The awkward array project is particularly suited for a CUDA backend because the operations really suit an array at a time approach that is common in the design of parallel algorithms that people write to be executed on GPUs. One of the main motivations of adding a GPU backend to the awkward array library is having faster operations in a lot of cases because you can parallelize a lot of the things. And something I want to address is our decision to target CUDA. So when we are targeting CUDA, it's actually just the first step to full GPU support. And we are not saying that we won't support any other GPU architecture in the future. It's just that we decided to start with CUDA because we felt that it is the most widely supported GPU backend right now. So if you look at the diagram on the right, you'll notice here that there are 3 layers. All of my work was at this layer under the extern C interface at the kernel level. And so the thing that I did this summer was generating this CUDA kernels block. And one of the things that allowed us to automatically generate the CUDA kernels was that the CPU kernels really followed a regular code structure. So the CPU kernels are written in C++, but when I say C++, it's basically C with template types. And the C++ functions that are present in the code base, they really look very similar. At least there are large subsets of functions that all look very similar. So it's easy to handle a lot of functions in the same way. And also we don't really use too many header files. So we don't have to go and parse the header files that are imported in the C++ file. And also, one of the main reasons we can automatically generate the CUDA kernels is almost 75% of the kernels that are present in the library are embarrassingly parallel. So speaking about the workflow, at the beginning of the summer, just the CPU kernels existed in the code base. And right now, we generate a specification from it. We generate CUDA kernels from that specification, and we also generate tests from that specification. So all of this is generated automatically, and all of this is derived from the CPU kernels that existed in the code base earlier. In the next week or so, at least within the time of my fellowship, we'll be tuning the specification that was generated and actually checking in the generated specification and CUDA kernels into the Git code base of awkward arrays. And in the future, the user would be writing the specification file, the CPU kernels, and the CUDA kernels. So you might notice that the only thing that is common to the block under existing kernels and new kernels in the future is the kernel test. So I want to emphasize the fact that the specification will always be used for generating tests for the CPU kernels and the CUDA kernels. And since we have developed tools that automatically generate the specification and the CUDA kernels, although we'll be checking in the generated files into the code base, we'll still leave them around so that the users could use these tools to maybe generate the specification of the CUDA kernels themselves, and then maybe tweak it by hand and before plugging it into the code base. And we're also exploring the idea of maybe using the specification that the user will write to automatically generate the header files, as well as the kernel dispatch that decides how to either use the CPU kernels or the CUDA kernels. So the specification that I talked about in the previous slide looks like this. I won't ask you to look at it too deeply right now because I'll be showing you this again in a later slide. But one of the things that you might notice from this specification is that there's this chunk under definition that looks a lot like Python. So just keep that in mind. And the specification is stored in a YAML file. And so you might think, how did we go from this C++ code that was used for the CPU kernels in the code base to this sort of YAML specification? So it involved multiple steps. The first step was translating the C++ code in the code base to C. If you look at this diagram on the right, you'll notice that, like I mentioned earlier, the code really is C with template types. There really isn't anything very C++ intrinsic that is not present in C, except from the template types. And we also have function specializations for having arguments for a kernel that have different types. And the reason why we are doing this step of converting C++ code to C is that simply that C is a lot easier to parse than C++. I know that C++ can be parsed maybe using Clang, but it's a lot more difficult than just parsing C. And the way we do this of converting C++ to C is using regex matching. So we replace the C++ headers, store the template type information, remove the template types, and store all of this stored information in some tokens that we can plug in later into the specification. So the next step is converting this C code that has been generated into Python. The way we do this is we create a CAST in Python from our generated C code using this tool called pycparser. And here you can see an example of how we have this C++ code on the left and we generate this Python code on the right. And this is a very simple function, but we can also do it for more complicated functions. And like I said in the earlier slide, we store a lot of things from this C++ code that we parse, like the types. So we represent these types that we have stored in the specification in our own sort of representation. As you can see here, we represent int32 arrays as list int32. So we are still not done with generating the specification. We also have to generate tests that we keep in the specification. So the way we do this is we annotate the header files for our kernels with Doxygen style comment blocks. So we specifically declare whether a parameter is an input parameter or an output parameter. Output parameter meaning that we expect the values of that parameter to change after being passed through the kernel. And based on these annotations, we pick up some values that we predefine in a JSON file. And there can be multiple values for a particular parameter. So we pick up each of them, and then we perform some combinatorics on these values. And this is not a very trivial problem because something we had to keep in mind is that we do not generate too many tests. And also so that we take up all of our memory, but also we do not generate too little tests so that all of the attributes of that kernel are not properly tested. So we perform these combinatorics and then we store these generated tests and their expected values in the specification file as well. And so that gives us the specification. Now you might take a closer look at it. You can see that in the beginning we have the name of the kernel, and then followed by the names of the function specializations, the types of the parameters of these function specializations, the input parameters, the output parameters, the generated Python, as well as the tests. So the primary reason for having a specification like this is to provide a correct definition for the kernel. So suppose the tests for the CUDA kernels and the CPU kernels do not match, then we actually say that the Python code that is represented here is the correct definition of that kernel, and the CPU kernels and the CUDA kernels should comply to the results that we would get if you would pass certain values to this Python kernel here. And for now, we are using the specification to generate the CUDA kernels. And so our process of testing is 3 steps. So we test the specification against itself. So we parse the test cases in the specification file, and then we pass these values as arguments into the Python kernel. And we test that the return result matches with the one that we have in the specification. Then we check if the CPU kernels and the CUDA kernels match the result that we got and stored in the specification. And if all the 3 tests pass, then great, our specification is correct. An added benefit that we get from having a specification is we have an automatic documentation generated. So from this specification, we generate documentation that we serve with strings. And this documentation that you can see here for the kernel that I've been showing throughout these slides is actually live right now in the Awkward Read the Docs website. And if you look at the page link here, you'll see that there's a whole bunch of kernels with their specializations and their function and their Python translation there on the page, one after the other. So we get to how we generate the CUDA kernels from the specification. So the primary thing we use to get the CUDA kernels is the Python definition and the type information from the specification. So we take this Python definition that we have, we use Python's AST module to parse the Python definition and create an AST from it. Then we plug in these types that we have picked from the specification, and then we generate CUDA from it. Here is an example of a trivial, embarrassingly parallel kernel. On the left, there's C++, or on the right, there's parallelized CUDA. And when I say parallelized CUDA, it really is parallel, and we are not executing the function on a single thread sequentially on the GPU. And so I have shown a very trivial example here. We can't handle kernels that are very complicated, but we can mostly handle kernels that are embarrassingly parallel. Right now, we can generate about 36 kernels out of 100. When I say 36 and 100, I mean each of these specializations counting as one. So when I say 36, that could well be 4 times that amount of kernels that we're generating right now. And we expect to be able to handle around 50 very soon. And it's not very hard. So when we are able to translate a particular kernel to CUDA, we are actually able to translate multiple kernels because, like I said earlier, a lot of them follow the same structure. So the development is in bursts where you generate CUDA for a bunch of kernels, then you try to generate one more kernel, and then when you're done with that, you get a bunch more kernels that you can generate. And we'll keep doing this till we reach a limit where we can't, where the kernels are too complicated to actually generate automatically the parallel CUDA code for it. So at the end of the summer, but it's not really the end because I still have a month left. The fellowship was extended. One of the things that I did during the summer was give a talk about my work on the Operator project to the Princeton University's Liberty Research Group. And I met all the deliverables, which are creating this kernel test generation framework, creating the specification automatically, going from the specification to documentation, and being able to automatically generate a lot of the kernels to CUDA. But there's still some things left before we can actually say that the GPU backend for Operator is done. So we have to complete the CUDA kernel test generator. We just have the CPU kernel test generator right now, but it's trivial to extend it to CUDA because we do using C types to do both. We have to tune the generated specification. So maybe add some more test cases, tune the Python that we are generating, things like that. For the kernels that we cannot automatically generate CUDA for, we'd have to manually write them by hand. And like I mentioned earlier, we are exploring the possibility of automatically generating the header files in the kernel dispatch from the specification. This summer, I merged 26 pull requests to master. It's not a very meaningful metric because I think 3 of these pull requests are huge and the rest of them were small ones, but it's still nice statistics to be able to stay. And yeah, thank you.
Thank you, Pratyush. Any comments or questions? No. Okay.
I have a
thank
quick
you.
question. Did you get any feedback from the compiler research group at Princeton?
Yeah, they gave us some ideas about how to do it, but actually the thing is, since we are handling a very specific set of kernels that follow a very regular structure, a lot of the advice that they gave us would is for more generalized problems. So they are more complicated than, let's say, for handling in a summer. So maybe that is something to think about in the future, but not right now.
Okay, thanks.
Okay. Anyone else? No, thank you again. Moving on. Oh, sorry. Was there another comment? Okay. And finally, our final presentation for today is Anish Biswas. It's going to talk about awkward away GPU kernels. Anish?
Yeah, I'll just share my screen and open.
Sure.
Are the slides visible?
Yep, you're all set.
Okay, thank you. Hi, I'm Anish. I'm a Google Summer of Code participant with CERN HSF. and I'm a junior at Manipal Institute of Technology in India. I've been working with Jim and Reik over the past few months, and over the summer, we extensively worked on developing an infrastructure to enable CUDA support for awkward arrays. Before I go into how we developed the infrastructure, it is probably worthwhile to talk about the initial challenges that we were faced with while drafting a design document for the CUDA integration. Although GPU support for awkward arrays was planned from the very beginning, when I started working on the project, there were a lot of places in the code base that made assumptions about the array buffers always always staying in the main memory. So fixing these up quickly became a priority. Then since we can't have users or developers compulsorily have CUDA on the systems to use awkward arrays, we had to come up with an intelligent solution to manage the dependency. And since a lot of the high level Python functions make use of NumPy, we had to figure out a way to provide a tight integration with CuPy, which is basically just NumPy, but with CUDA support. So the basic idea behind the integration really lies in the 3-layer architecture of awkward arrays. The multiple layer helps in introducing indirections going from the upper layers to the lower layers. And with a high enough level view, you can think of it as calling appropriate modules instead of individual functions. So if you look at the diagram, how the C++ layer interacts with the C kernels actually demonstrates that idea of indirection pretty well. Also, there are largely, due to the largely symmetric view of the entire awkward arrays, we can write parsers, which would just parse the CPU kernels and generate GPU kernels in bulk instead of writing 100 plus of such functions by hand. Okay, now coming back to the actual infrastructure, the first milestone in having a CUDA backend would be to have array buffers that exist on the GPU. So this is how you would declare an array on the main memory using awkward arrays. Now, if we view this as an STL C++ vector of different class instances, just because they are all different, it would become pretty difficult to transfer this all onto GPU using CUDA, since each thread would have to do a different amount of work, and we'll have to synchronize the threads again and again for correctness. This would instantly defeat any purpose of having a GPU support, just because synchronization eats up a lot of compute time. But what if we could have a linear view of the complex data structure and let CUDA do what it does best, that is operate on linear buffers? The diagram illustrates the idea pretty nicely. At this point, it would probably be very helpful to think about awkward arrays as a tree where its leaf nodes are either the NumPy array class or the offsets, which are in red and blue. And those are essentially just index classes. This way, we would only have to ever work with linear buffers instead of just looking at the entire complex data structure at once. The next slide elaborates on this idea more appropriately. Here's how the array would actually look inside the awkward array ecosystem. The outer offsets control the jaggedness of the array, which are in turn just linear buffers. A similar format follows as you travel down the array. The fields X and Y are flattened views of the jagged structure you saw in the previous slide. Now, transferring this entire structure onto the GPU can be done very conveniently by using awk.to kernels, brackets array, comma, quotes CUDA, and where awk is just an abbreviation for awkward arrays, and you get something like this. So yeah, that's your entire data structure on GPU. If you notice the bold fields, the fields in bold, you'll notice that only the leaf nodes, the index class or the NumPy array class, got transferred onto the GPU. You have a device number and a device name, which as an indication of where the buffers actually reside. And this is actually for a future development where we would have a multi-GPU support, and it would be completely confusing if you don't know which buffer exists on which device. So this entire problem of transferring buffers onto the GPU really becomes just a simple recursive walk down the complex data structure, where the base case is just transferring the leaf nodes onto the GPU. Moving on. So to track the location of an array buffer, we assign a new enum class type to each of the leaf nodes, that is the NumPy array class and the index class. It's worth talking about the fact that the users have complete control over where the array buffers reside. That is the main memory or the GPU memory. We avoid any kind of behind the scenes transfers, which might actually slow down the library during runtime. Now that we have arrays that exist on a GPU, we can now handle the CUDA dependency. The command to install awkward1 with CUDA support is just pip install awkward1 and in brackets CUDA. The brackets CUDA instructs the pip installer to fetch the awkward1 CUDA kernel's pick package, which is just an extension to the awkward arrays, which would just enable the GPU support. And the important part here really is the fact that awkward1 CUDA kernels is just an extension and not a dependency. And the awkward1 CUDA kernels package itself is very lightweight and consists of init Python file and a shared library. This shared library makes the entire package very portable and very easy to install across all Linux systems. So let's talk about how we would handle the extension or the shared library. We make use of Linux system function calls like dlopen and dlsim. Dlopen, given an absolute path, returns the handle of the shared library, and with dlsim, we can call the functions or symbols in the library. Now, one potential disadvantage of having such a system is that it would be pretty difficult to write and maintain 100 plus such calls, which are largely similar. So we don't do that. Instead, we just rely on the preprocessor to do the entire work. Here we have defined a macro called create kernel, which takes in the CPU kernel counterpart, and it reduces the argument list using the C++ declaration type. And we cast our void function pointer using that. And this entire macro just mitigates the process of writing 100 plus such function calls into one single macro. Now that we have arrays that live on GPUs and have good mechanism to access the shared library of the awkward1 CUDA kernels with package, we should think of a dispatch mechanism which would call the appropriate library based on where it lives. Here's a very generalized pseudocode of how the 100 plus function in the kernel dispatch file look like. These all return an error struct and have a libenum class type as their first argument. And this lib type actually tells us which kernel library we need to invoke. Since the CPU kernels are already baked in awkward1, you'll call them directly. But for CUDA kernels, you'll have to use the macro create kernel and then use the function pointer, which returns the value, which calls functions basically. Now that everything has been done, we have a full working infrastructure that supports GPU arrays. Now let's visit the same array that we took a while back while discussing about transferring buffers onto the GPU. Allocating this buffer on excuse me. Allocating this buffer on the GPU is as simple as adding an additional parameter called kernels equal to quotes CUDA to the constructor. And that's really all you need to do to have the array buffer on the GPU. So let's start with a simple example and the stuff we could do with this buffer on the GPU. So a simple awk.num would just count the number of elements in each axis. So here you have 3 for the first list element, you have 3 records. For the next list element, you have 0 records. And for the last list element, you have 1 record. So you'll have a buffer which says 3, 0, 1. And we can also do some pretty non-trivial stuff with this. So what if I said that I need to do I need to find the number of elements in each list for every list of field y. So basically this y field, and I need each element which exists in each of these lists. So this would return a jagged structure once you do an awk.num on array subscript y on axis 2, and you'll get, so this has 1, this has two lists, this has 3, and this is entire 1 list, the outer list. So you'll have this 1 element. The next one has 0 such fields, so you have nothing, and the last one has 4 and 1, so you'll just have that 4. And everything that awk.num does is native to the GPU, so there's no internal transfers going on behind, and this is all utilizing the GPU support. So you might be wondering, okay, you just showed me one function, awk.num. What about the other functions? So yeah, I did work on just 2 kernels, awkward list array num and awkward regular array num. And I created the entire infrastructure, which actually does these 2 operations and supports all the 100+ kernels in the future. So so we made sure that if these 2 kernels work for all cases, which it does right now, then Reik's parser produces all the rest of the arrays in bulk, and that would really just be plug and play. And this graph actually demonstrates that. So somewhere around June, I had got this kernel written, the num kernels, and till then it was constant. And like just a few days back, Reik completed his first batch of automated translated kernels, and they just went into the repository easily. And now you can use multiple kernels too. Lastly, awkward array has a strong integration with CUPy now. CUPy is just a mirror of NumPy, but for CUDA. So CUPy uses GPUs to perform a lot of functions of NumPy, and they are very symmetric altogether. So, and they have pretty good documentation, so you could just check out the website for more information. And so here are some examples that demonstrate the idea of CUPy with awkward arrays. So you can construct an awkward array from CUPy just as you would do it for NumPy arrays. And here, CP is just an abbreviation for CUPy arrays. So you do that and you get a awkward array. Now the important thing to, or the interesting thing to note here is that these buffers declared by CUPy are actually still owned by CUPy, and awkward array just wraps it around it, wraps the buffer around the awkward array ecosystem, and there's no internal transfer going on. And a very similar example going from awkward array to CUPy, we declare an awkward array on the GPU, and we call CUPy.asArray, just as you would call NumPy.asArray, and that gives you a CUPy buffer. And even here, this buffer is actually owned by awkward array and not by CUPy. So CUPy here acts as a wrapper, and there's again no internal transfers going on. Yeah, so that concludes my summer of code. Over the last 3 months, I managed to nearly meet all of my deliverables. I can now track memory location through the awkward array classes. Then operations involving CPU array and the GPU array is being handled intelligently. We developed a deployment strategy for users with GPUs and users without GPUs. And finally, we integrated CUPy with awkward arrays. And although it's a funny statistic and doesn't mean much, but over the 3 months, I managed to push around 22,000 lines of code to the master branch of awkward arrays. So yeah. And yeah, that concludes my talk. Thank you.
Thank you, Anish. Anybody with any comments or questions? No? All right, I just want to say thank you again to all the fellows as well as all the mentors. You know, producing this despite the pandemic is a pretty good achievement. So just want to thank you all again. So, and that's it for today. So thank you.
Thanks, everybody. Great work.
Yeah, pretty amazing work. Thank you.
Bye.